sure, and you have to ask TAs. Should be fast though, so that you can get some feedback before the second one is due. That I cannot guarantee. Yeah, especially the head TA for programming, he's looking for jobs now, so I'm not sure. It really depends on his schedule, whether he's very busy. But I'll try to push him a little bit. Oh. All right, let's get started. So last time, we discussed the basic structure of a neural network, this layer structure for deep learning. When deep meaning you have many layers. And we saw that to calculate the estimated label of any input, we send the input to the first layer, layer 0, of the neural network, and then you do calculation layer by layer until you get to the end, and the end you get the estimated label, right? And how good is that estimated label? Well, you compare the estimated label with the true label, whatever error metric you want to use, squared error, loss function, whatever, right? You can find a metric of error. Then the question is, how do we design a good neural network? In other words, the weights, the parameters have to be good, the W's have to be good in order to minimize this error function, right? Okay, and to do that, we saw, well, we can use gradient descent. That means that we have to find a way to compute the gradient. And last time we saw that if you use the conventional way of computing the gradient, turns out that the complexity is O of Q squared, where Q is the number of weights or number of parameters that you have to optimize. And we saw that the Q, the number of parameters that you have to optimize, is huge in general, yeah, for millions upon, more likely billions of parameters. So OQ square turns out not to be realistic, yeah, not acceptable in reality, yeah. We have OQ square because every forward pass, forward propagation has complexity of OQ, right? The number of edges, which is clear, you know, at least you have to compute those things once, right? So at least it's OQ, it cannot be smaller than that, actually. So it turns out that if you want to take the finite difference to compute gradient, you have to do this Q times, because every weight you have to do that once, and therefore you have OQ squared, right? Not acceptable forward propagation. But just to review the notation that we use, we continue to use the same notation. We have these weights of the multiple layers all the way until the L. Each one of these is a matrix, right? The multiple matrix. And we have a loss function that we need to minimize, which is En of omega with respect to the nth sample point. Yeah? One example would be just some kind of a comparison between this output vector that you have with the label. The output layer could be the probabilities of the label that you estimate, right? A cat or a dog with certain probability, and then you take a maximum of that, and then you get the estimated label y hat, yn hat, then you compare with that, yeah? Okay. Or you just directly use a lot loss function. So again, we want to compute this partial derivative with respect to all of the weights, right? So for all I, J, and L, yeah? And that's the challenge. So forward propagation method does not work. And then, of course, you have all heard of the term, I hope, right? In other courses, back propagation, yeah? Instead of calculating things from layer 0 to layer L, capital L, we go from the back, a layer capital L, forward, okay? That way of calculation turns out to give you, will give you big O of Q complexity to calculate these, the gradients, okay? So we're going to go into this in a bit more detail, probably, than what you might have seen in another course, yeah? So today will be a bit more math heavy, yeah? Quite a bit of algebra. But it's not too bad if you're comfortable with your calculus, in particular your multivariable calculus. So it's a bit, yeah, calculus 103. So the backpropagation algorithm is a form. It is a form of dynamic programming. Yeah. Similar, anyways. So the idea is already known in the 1960s. Okay, but people did not really apply it to neural networks for a long time until people get to the point when the neural networks becomes too large to handle, I guess, yeah? So it's actually the idea is so popularized, not at the beginning, it was so not popular, but popularized by, after this paper, a paper in 1986. And guess what? One of the authors of that paper is our very own Jeff Hinton, yeah? And so one of those things that he has done that established him as one of the foremost pioneers in deep learning. Okay? So how does it work? We're going to have to, again, our objective is to calculate this partial derivative, right? For each one of these weights, we have to calculate that. And so it's backpropagation. So first of all, let's just say that since we are going to do this for all sample points, we're going to skip this n because otherwise there are too many things to write, yeah? So because this is the same analysis for any n, right? For any sample, yeah? For any xn, yn anyways, yeah? So we're going to just drop the n just for convenience. Now, in a nutshell, instead of going forward, we're going to do backward calculation, and layer by layer, we're going to keep track of a quantity that we're going to denote by delta. That's a vector of L. For the else layer, we're going to have a vector called delta. Yeah, we're going to define delta. No worries what it is, but the main idea is just do this. We keep track of this delta vector. Okay, so therefore, right now we're going to say, well, what is the role of delta? Yeah, we're going to define it soon. Okay, we first define it, and then we discuss how to compute it in an efficient manner. Yes. In a way, yeah. You just because this layer is all connected, right? So you can go forward, you can go backwards. They are, turns out that the relationship going backwards is easier to handle. That's all. So before we know what this delta is, let's note two things. First of all, this error E omega has this so-called memoryless property. Okay, what do we mean by that? Memoryless. So E of omega. Well, first of all, just write it out. Just write out the omega. Yeah. So W1, W2, WL. Right? These are all of the parameters that we need to decide, right? Now, but you remember, it's in this layer by layer structure. Okay. By the time that I get to layer L, okay, in order to continue to calculate E of omega at the end, I can forget about what has gone before it. Yeah, the W is before this point. I can forget about it. All I need to know is what SL is at this point, right? This SL in this stage contains all of the information that we need in order to calculate E omega, right, going forward. Yeah? So I can forget about the past. Yeah, that's the so-called memoryless property. Yeah, in the calculation of E omega. So if you want to write this idea, I think the idea itself is okay, right? It's layer by layer. So once I get to layer L, I can forget about the earlier layers. Yeah, simple idea to express that mathematically. So basically saying that this E is a function now of S of L at the L's layer. And after that, all the work I care about is W of L plus 1, all right? And then all the way until the end. I don't need to know what is before, yeah, the earlier W's anymore. Yeah, makes sense, right? Clear, yeah? So again, this contains all information that we need. All info up to layer L, right? Yeah. So, and let's break this down. This vector S is the input into the neuron, right? Remember our notation from before. S is the input into the activation function. Yeah, it is a weighted sum of the previous outputs, yeah? And then you send this to an activation function, and then you get the output for the next layer, right? So S is the vector of input for the current layer. Yeah. So therefore, there is one input for each neuron. Yeah, I can write it as S1 of L. Yeah, and then let's say all the way to the J's node, the J's neuron. Yeah, until and then the N, which is there are how many neurons are there? D of L neurons, right? The N is D of L. Yeah. And then layer L. Yeah, and then the rest is L plus 1. WL, yeah? Okay, so we can rewrite the error function in this form when we get to layer L, yeah? So now let's focus on one of these guys, Sj, see what it looks like, okay? So that's note number 2. Sj of L, of course, is the weighted sum of the previous layers. So it is the bias term times the weight of the bias, and then k goes from 1 to d L minus 1. Right? That's the previous layers. Yeah, it's a weighted sum of the previous outputs. So xk of L minus 1, right? Multiplying the weight at k between k and j of L, right? Remember our L indicates the layer of the destination, right? So it's L. Yeah? If this does not look familiar with you already, then one way to see this is drawing the picture again, right? We've seen this picture again. I'm just drawing that part that's relevant, yeah? This input sent into this J's neuron in the L's layer, yeah? And then you output XL, right? This is node J in layer L, just in case you've forgotten the power notation already. So this input is the weighted sum of the information from the previous layers. So you have all of this coming in, yeah, from different neurons. In particular, one of them is XI, let's say, XK, let's say K, yeah? Well, let's say I, because we are particularly interested in one I. And then you multiply the weight, yeah? Like that, right? And then, you know, there are multiple of these guys like that, sum up together, get to this neuron, okay? So what you observe here is, again, keep in mind our objective. We want to find this derivative, right? Derivative of EM with respect to WIJL, yeah? Where is WIJL? This guy here, yeah? WIJL right here. We want to find the derivative with respect to this guy, yeah? But then we know that this one would be a function of something, becomes this SJL, yeah? And then get to the error, right? You just keep going forward, you can get to the error, yeah? So you think I want to find the derivative of the error, that function there with respect to this guy, then we can view this E of omega as a composite function of this guy, right? Composite function in the sense that the E of omega is a function of S, and then this S is a function of this W, right? Therefore, there's a differentiation by rule, the chain rule of differentiation that we can use, yeah? In particular here, you notice that this one, how does this information get sent to the final destination, the E of omega? Only through this path, right? There's no other path where we will use this weight, yeah? Only through this guy, Sj. No other neuron will use this information of Wij, yeah? So then the chain rule will be the simple one, yeah? So we know that in the entire vector, all of the neurons, only Sj of L depends on this weight that we care about, yeah? Depends on Wij of L, right? No other neuron will use this weight, yeah? So, and therefore 1 plus 2 is memoryless, so we only have Sj, right, on top there, and then this is a function of Sj. Sj is a function of this W, yeah, and no other variables is a function of this Wij, yeah, no other function. So therefore, I can write the partial derivative E of omega Ij of L, again by the chain rule, as partial. So this is the easy one. Later, we're going to look at a more complicated one, okay? So let's make sure that we are all on the same page on this easy one, yeah? Sj of L, and then partial, oh, I'm sorry. I messed up. This is partial Sj, of course. This is composite function, yeah? Wij of L. Right? No problem so far, yeah? Simple composite function, and you take the chain rule. And what is this equal to? Well, the first term, I don't have any idea yet. I'm going to just write it down. And then what is the second term? Yeah? Yeah, exactly. You look at the top line, right? What is the function of Sj with respect to Wij? Yeah? It's simply a linear function, right? Linear function of Wij. So when you take the derivative, you just get whatever coefficient in front, which is xk, or xi in this case, xi L minus 1. Yeah? So xi L minus 1. Yeah?
The idea then to try to find the first
Yes, we need to find that. Yeah, that's what we're going to define as our delta that we're going to go backwards. So we're going to define, and this term is very important, delta J of L as this guy, this partial derivative of the error with respect to the input into the J's neuron at the L's layer. Okay? So you can view this as the sensitivity of the error to the input at this layer, right? Sensitivity to the input. Okay? So that's how we might interpret this, the meaning of this term. This delta is the sensitivity of the error to layer L input, not the output, right? The input to that layer. Yeah? Okay. And once we have this, we can rewrite this the one above, which is says that if you want to find the partial derivative with respect to the weight, which is our ultimate objective, yeah, this one is equal to xi of L minus 1 times delta J of L. Okay? This is one of our central equations. Yeah? And since there are so many of them, I and J, we would like to combine them in a compact way by writing a matrix vector multiplication form. Yeah? So we simply define, let's say, this of all of them. Yeah? So this is a big matrix, right? You can view it kind of almost like the gradient with respect to the Lth layer weights. Yeah? Same with the collection of these partial derivatives. It's a matrix now because big W is a big matrix, right? Yeah, and the I, as we have seen before, goes from this to D L minus 1, and then J goes from 1 to D of L, like that. Yeah? Okay. So, and then we further define, let's say, right here, yeah, why not? This xl minus 1 vector as, well, x0 l minus 1, that would be the bias term, right? And then x l minus 1, and then this is dl minus 1, right? They're all together dl minus 1 neurons from the previous layer, yeah? And then we also define this delta L in this one. Well, we are not going to have a bias term, of course, because this one has to do with the input sensitivity, right? The bias term is not part of that input. D of L. Again, it looks a bit messy, but then once you see the pattern, really it's quite straightforward, right? Yeah. Just stack them all up. Yeah. Then once you write this, now you see that this term, yeah, for any ij, we have a product like that. If we put them all together in the big matrix, to get the matrix, you multiply a column vector by a row vector. Yeah, then you get the matrix. So then we're going to have this with respect to the L's layer big matrix is equal to xk minus 1, oops, L minus 1, multiplying, well, this has to be the vector of L, yeah. Except that we have to take the transpose because otherwise we don't get the row vector. Yeah. So again, notice that this is a column vector by definition. Our convention is to use column vectors, and therefore transpose is a row vector. Yeah. Again, from a linear algebra, when you multiply a column vector by a row vector, you get a matrix. Yeah. So that's exactly what you want. So the gradient with respect to this matrix. Yeah? Okay. So therefore, we know that in order to calculate this gradient, which is what we want for all different L values, different layers, our ultimate goal is this. We know now that we can write it as this output multiplying this delta, which is sensitivity. Okay? This one we already have because you just run a forward pass, forward propagation, you already have all of these values. Yeah? Okay, the S and the X's we already have. Yeah? This is the one that we don't have. We need to calculate at this point. Okay? So now the next step, of course, then is how do we calculate this in an efficient manner? In the end, we're going to have a method that does it in big O of Q complexity, right? And that's the back propagation. Yeah? We calculate this layer by layer from the back. Yeah? So the next one is to compute delta of L backwards. Yeah? Okay, that's how do we do it. So turns out that there's a nice way to do it. So first of all, you want to find the delta of L for the last layer, right? From the back. So for this analysis, let's suppose that the last layer will only have a single neuron, okay? But you can easily generalize this to multiple neurons at the last layer. But it just be a bit more tedious. So let's just assume that this is equal to 1. Yeah? It's only for simplicity. It does not change anything. Simplicity of demonstration here. So 1 neuron, then you will see that, well, this thing comes in as of L, yeah? And then this one gives you X of L, yeah? One-dimensional. And also, for simplicity, we're going to assume that this theta is the same theta as all of the other theta, so we don't, write a different theta for this, so that it just makes things more confusing, but doesn't help really. Yeah. Suppose same as the rest. Yeah. As the rest. Yeah. Again, only for simplicity of illustration. Now, once you have this this is basically the output of your neural network, right? So now we're going to compare that with the true label to get the loss function, right? Remember we call it G function, right? Whatever it is, doesn't matter, yeah, of Y. And then this, by definition, will be our E of omega, right? Yeah. Again, we drop the subscript of n because for every sample n is the same thing. Okay. So now we want to find this delta of L, right? The first one. And by definition, this is the sensitivity with respect to the input to the last layer, right? So just sensitivity to that input. And because we already know that now at this stage, this is equal to X of L compared with the true label Y, yeah? And so this is partial of S of L, yeah? Okay. And what do we do here? Well, again, it's a composite function, right? X is a function of S, yeah? So this is another composite function. Take the derivative, the chain rule differentiation. Again, this is the easy case. We're going to see the harder case later. So enjoy the easy time as much as we can. So far, so good, right? This is okay? Everyone is okay? Yeah? And then this one, well, whatever it is, yeah, depending on what G is, right? Is it a square loss function? Is it a log loss? It depends, right? So doesn't matter. And what is this one? Second one. How do we know what this is? The first one? No, it's easier than that. It's already on the screen. Oh, yeah? You should know already what is this. Yeah. Yeah, theta, but theta prime, yeah, theta prime, yeah. So it's the derivative S of L, because x is simply, a function of S, in terms of theta. So it's that's all that we need to do, yeah. So all of this can be computed easily, yeah. Well, for example, let's say, well, let's squeeze in the example here. We have linear regression at the end, yeah. You use a linear regression at the end. Then G of L, Y is, we use the square loss, yeah, right? Then what is delta L? Just derivative of this thing with respect to XL, right? Easy, it's a square term, so it's a 2 times x of L minus Y. That's it, right? And then multiply theta prime S of L, yeah, whatever theta is. And for example, let's say theta is your common hyperbolic tangent, TANH. Yeah. Then what happens? Your delta L will be equal to 2 times x of L. Again, you have x of L, right? Because you already passed through the forward propagation once. You get to the end already. You know what x of L is. And then what is theta prime? Remember, for the hypotangent is 1 minus theta squared, right? So that's a very nice property about the tangent. So theta squared is simply hyperbolic tangent square, yeah, of S of L. Again, S of L you also have, yeah. In the forward propagation, you already have that in the current stage. Okay, so that's it. You know how to calculate the delta for the last layer. Yeah, we're done. And now we just need to figure out, how to go back. Okay, so this if you think about this as almost like the induction, yeah. This is just going backwards. So now we have the base case. We have to reduce the layers going back. Yeah.
Like if we have like multi-neurons in the last layer, do we like calculate like separately and then add up all of them, or like we just?
Oh, then you're going to have a vector here, right? Each element can be calculated in the same way. Yeah. So. Okay. Number 2. So for intermediate node now. Intermediate. So we want to calculate delta I of L. Okay. Now, what is delta I of L? Is the sensitivity of the error function to the L's layers input. Yeah. So let's say we have this input, L's layer, Si. We just have to know the function of E of omega, what kind of function it is with respect to this input, right? Yeah, so that we know how to take the partial derivative. So this one comes out as xi, yeah, and then it gets sent to the next layer, right? So the next layer, let's say like that. There are multiple neurons. Let's say there's one neuron, second neuron, until the last neuron. Yeah, and then all of this gets sent to the other layers, right? So this one would be the input to the next one. So S1 of L plus 1, right? S2 L plus 1. And so on. I'm not going to write down this one. Yeah, it's just S of D L plus 1, L plus 1. Yeah. So all of these things will contribute to the E of omega at the end, right? All of them will contribute to the end. So this is going to be the dependency of the error function to this one is more complicated now. Yeah, there are multiple paths for this information to get to E of omega. Yeah, so this is a rather complicated composite function. Yeah, because there are multiple variables here that depends on this guy that we eventually get to E of omega. Yeah, so it'll be complicated. Our chain rule of differentiation will be the more general form that you might have seen in multivariable calculus, but who remembers those formulas, right? So I want to remind you, yeah? Yes. It's going to be a scalar. Well, this is a scalar, right? The delta? Oh, no, delta. This is with respect to the ice node, right? Oh, the last one. No. In general, you might have multiple outputs for your neural network. Then you're going to have a vector. But you do the same calculation anyways. Yeah. So now the question is, how do we calculate this delta I? Of course, the idea is to go backwards. So at the layer L, we assume that we already have the values of delta for the next layer, L plus 1, already, right? Because we come backwards. And we already have that last A layer anyway. So we just keep backtrack. So at this stage, just remember that at this stage, we already have let's say delta L plus 1, right? As a reminder, what is delta L plus 1? The delta J of L plus 1 is equal to the partial derivative with respect to Sj of L, right? Oops, L plus 1, sorry. Yeah, we already have this, all of this vector, yeah, by this stage. But what is this? This is nothing more than the derivative of E omega of these items here, right? Yeah? So basically, we already have the partial derivatives with respect to these guys. Now we want to use that information to find the partial derivative with respect to this guy. Yeah? Everyone see that? Again, at layer L, since we're backtracking, at layer L, we have delta for the layer L plus 1 already. And the delta for layer L plus 1 is simply the partial derivatives with respect to these guys. Yeah, by definition. The partial derivative with respect to these guys. So now the problem, our mathematical problem is the following. Given that we have already the partial derivative with respect to these guys here, how do I find the partial derivative with respect to this guy? Yeah? Okay. So let's see. Let's write down delta I of L is equal to, well, again, by definition, delta Si of L is equal to, that's one more step, since we have an intermediate variable there, Xi of L, yeah? Let's do that, one more step of chain rule first. Xi of L, yeah, Xi of L, because we know how to find this second partial derivative very well, yeah, right? Again, this is simply equal to the first term. I'm just copying it down. Nothing new here. And then for the second term is theta prime of Si of L, yeah? Second term, I already know how to do it, how to find it, yeah? So now it's really the first term. Yeah, partial with respect to Xi, yeah? But again, this one, Xi, goes all the way to E of omega through these multiple paths, yeah? There are multiple pathways to get to the end. So now we have to use a fancier chain rule. Okay. That says, if I have a function, let's say z is equal to a f of xy, but then x itself is a function, say g, of some other variables, s and t, yeah? And then y is also another function, h of s and t, okay? Then what is the chain rule? The chain rule is partial z, and then partial s equals to what? Anyone remembers this kind of thing? It turns out that it is partial of z, partial of x times partial x, partial s, plus partial z, partial of y times partial of y, partial of s, like that, okay? You have to make this sum, okay? because now the Z depends on S through X and Y, through two things. You have to add them up together. If there are more things there, you just add more things. Okay? Just this is a general rule. And of course, if you want, if you want to calculate partial of Z, partial of T is the same thing. Yeah, I'm not going to write it down. Yeah, so it's just say. So this is from your multivariable calculus. Now, in that case, then I can write this. That's what we want to calculate now, right? Yeah, and I know that this one impacts all of the S's, right? Yeah, this XIL there goes through all of these S's in order to get to the final formula, yeah? This composition is exactly this form, yeah? Except that now we change this XY to all of these S values at the layer L plus 1. Yeah, everyone okay? So just a big sum of these partial derivatives, yeah? J will have to be equal to 1, and then no matter how, just how many, L plus 1, yeah, at the layer L plus 1, how many neurons you have. Each one of them, you have to do this partial Sj of L plus 1, yeah, and then times partial S L plus 1 Sj, yeah, and then this is J, partial Xj at L, like that. Yeah? Just the same formula, yeah? The chain rule of differentiation when you have dependency through multiple variables. Okay? But again, we are in luck because we already have the first term. Yeah? This is simply delta J of L plus 1. Yeah? We already have from our back propagation. How about the second term? What is the second term? Again, look at the picture, right? What is the relation between Xj and the S in the next layer, yeah? How do we find this derivative here, given that picture there? It's simply a xi multiplied the weight, right? You get to that one. So all of this would be the weight. Okay? So the linear function. So we simply write this as, oops, okay. Wij, just the weight in front, L plus 1, yeah? Okay, that's that, right? So this tells us that, remember again, that this is a derivative with respect to xi, but our ultimate goal is to find derivative with respect to si, right, the top line there. So we already figure out how to find the first term, then just multiply by theta prime, yeah? So we write this down, and we have delta I of L is equal to this sum, 1 dL plus 1, delta J, L plus 1, Wij, L plus 1, this whole thing multiplying theta prime of Si of L, yeah? Now we are pretty much done, right? We figure out how to use the delta, the input sensitivity in the L plus 1 layer to calculate the input sensitivity at the Lth layer. Yeah? Okay. What remains to be done is just to make this look nicer by putting things into matrices and vectors so that we have a clean form to look at. That's all. Okay? So again, we define these things. Wow, I think we already written this once. But anyway, let me write it out just for cleanliness. Yeah, like that. The next one is new. We're going to define a W hat of L plus 1 that contains all of the weights that goes into the layer L plus 1. Yeah? But the weights, for this particular matrix, we're going to drop the bias weights, unlike the previous one. The W that we have before, the big W before has the bias weights. But if you notice this line, how we calculate delta I, we don't look at the bias weights, yeah? The bias weights don't show up here. Yeah, okay? So we're going to write this matrix without the bias weights. So 1, 1 of L plus 1 all the way to W1, and then DL plus 1, yeah? And then all the way this one, I guess DL of 1, L plus 1, da, 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 W DL, yeah, D L plus 1, just a messy writing, that's all, right? The pattern should be quite clear. Yeah. And as I said, this is same as the W of L that we have before, L plus 1, sorry, L plus 1 before, except that we don't have the bias weights, yeah? So this is the same as that one without bias weights. Okay? So nothing mysterious about this new W hat, yeah? And we still need one more vector to fit that the theta prime. So we're going to define theta prime of the vector SL, yeah, just by definition as this vector of theta prime S1 of L, yeah? And then all the way to theta prime of S of DL, yeah? Of L, yeah? Okay. Again, a lot of this at this stage is really to keep track of the indexes, make sure that your accounting is correct, that's all, yeah? There's no mystery there. Yeah? Just have to have patience to keep track which layer, how many neurons are there in that layer, what symbol we use for that, that's all. Once you write these together, to express the line on top in a compact form, we simply write this, all of them at the else layer, turns out to be equal to W hat of L plus 1 multiplying this vector at L plus 1, okay? And this whole thing now is a vector. This symbol represents pointwise or pointwise multiplication, S of L, because both of them are vectors, right? We have a vector multiplying a vector. This just indicates that we do pointwise multiplication, that's all. Yeah? And this is our final form for backpropagation. Yeah? Okay, now I have to be careful. Don't mess up. Where does it go? Ah, okay. Yeah. So I hope everyone is convinced, semi-convinced at least, yeah, that this one is a matrix representation of those, the top line there, which is a ij, individual element representation. Yeah. Again, the idea simply is that now we can go from the back to the front, to calculate this layer by layer backwards. All that we need is to have this delta. And remember, why do we want to calculate this delta? If you remember all the way back, this delta simply is an element in here, right? If I may, I'll come back to there for those who have not finished copying yet. Here, yeah, because this guy on top there, yeah, only requires us to know what delta is. Yeah, we already have x, yeah? And now we find a way to calculate delta backwards. Now, once you have delta, then you can plug it in, and then you get the gradient that you want to calculate. Yeah? Okay? So therefore, we are done. Yeah? So once we know how to calculate delta, we are done, pretty much. Yeah? So this is the famous backpropagation for neural networks. Okay? And with all of the details. Yeah? Again, it's a bit just messy, and the only challenge, there are two new things here, right? First of all, you calculate things from the back. Second challenge is that this multivariable composition, multifunction composition for the chain rule, that's all. Yeah? The rest is just, small algebraic manipulation. Okay. So we'll continue next time to put this backpropagation algorithm all together, and maybe take a quick look to convince yourself that indeed the complexity of this is big O of Q instead of big O of Q squared. Okay, huge difference, right? And then we'll look at an example how to use this. Yeah, and then also some implementation issues when we have to implement neural networks and how to apply them neural networks in reality. Yeah. So we stop here. See you next time.